This video we're going to do a basic summary of Units 3 and 4 where we looked at atomic theory and development and light and electron configuration. So, taking us way back, we had Democritus throwing out the idea of atomos, which meant indivisible particles, and that's what we now call atoms. But for a long time that got put on the back burner because of a more popular philosopher with a different point of view, and then eventually got picked up again later by Dalton, who came up with modern atomic theory, which included the law of conservation of mass, law of definite proportions, law of multiple proportions. Look up what those are. So his idea was that atoms were like little billiard balls. And that was a great idea. It was a good starting point. But it's not valid because if that were the case, all light would be scattered by the billiard balls and everything would just look gray and grayscale. But that's not the case. We obviously know we can see other colors in that. Then came along Thomson, and he came up with the Plum pudding model of the atom, where he recognized that, there were tiny little electrons, and discovered that those were particles using these cathode ray tube experiments, and then came up with that idea that there was a positive charge spread out throughout the atom, and that there were these tiny little electrons. And so if that was the case, what would happen is essentially the electron would be able to only absorb and emit UV light. So that's not really valid, and that's not what happens. So then came along the idea that maybe it looked like a solar system, but that goes kaboom. And then Bohr's model came along, and his big revelation was that the electrons exist in specific energy levels and can only gain or lose energy in discrete chunks called quanta. So you can see here that this is the electron right here, and it's traveling in a certain path. And it absorbed energy. And then it releases that energy in non-gradual progressions. And this is where quantum physics kind of came to be. So the electrons lost that energy in one discrete chunk and emitted that energy as a photon of light. The bigger the difference in the energy of where it is when it's excited versus where it falls back down to is going to represent the light that's given off. So we know that all light travels at the same speed, the speed of light, 300 million meters per second. And when you're looking at the properties of light, you have two main ones that we look at. We look at wavelength, which is how the distance between identical points on adjacent waves, and then the frequency, which is how many times it cycles up and down per second. So those two quantities are inversely related to each other. And we also know that the faster it's moving up or down, or the higher the frequency, the higher the energy associated with that photon. So the energy drops you see occurring with these electrons are going to be directly related to the energy of the light that's given off. So the bigger the drop, the higher the energy of the photon, and the shorter the wavelength, and the higher the frequency of that photon. And then, after Bohr's model of the atom became a little bit more descriptive. They don't really travel in these specific orbits like that, and electrons aren't truly just to be thought of as particles. Louis de Broglie came along and said that the electrons really behave more like waves. Everything actually is a wave-like nature. It's just much more observable for smaller things like electrons. So they're really wave functions that happen. All right? And they get excited, and then they come back down to the ground state and release the energy. And Ernst Schrödinger came along and kind of gave it more of a three-dimensional component where he came up with basically what we would call our orbitals today. So let's take a look at how that impacts the periodic table. So on each of those energy levels, we really have different subshells or orbitals that exist. For a simple atom like hydrogen, you can see that there's only one electron. And this is the Aufbau diagram, which electrons go in the lowest energy orbital possible for hydrogen. So it only has one electron, so it's going to go in the first energy level. The first energy level only has room for an s subshell, which has one orbital and can hold a maximum of 2 electrons. That's why our first row in the periodic table only has 2 elements, because the second element has 2 electrons, and after that, that energy level is complete. Now, the periodic table is arranged based on the electron configuration. That's not how it was created. And that kind of points to the significance of electron configuration. So the properties of any element is directly related to its electron configuration. Because Mendeleev put this whole thing together based on repeating properties, or a periodic law he noticed where these elements all behave similar, these elements all behave similar. But it's because of their electron configuration. So First energy level, only an s subshell. If it has two of them, it's full. You can see that the next electrons are going to have to move up into the next energy level. And therefore, any atom with 3 electrons is going to start filling up its second shell. Now the second shell has room for more than just the S subshell. It has room for an S and a P subshell. So the S subshell holds 2 electrons. Once that gets filled up, however, the next electrons have to go in the 2p. And you can see that the second energy level, P subshell, is way over here. This is known as the P region of the periodic table. So the first element has 1 in the P, and then 2, and then 3. You might notice that 1 electron went in each of the orbitals before any of the orbitals had 2 electrons. So that's known as Hund's rule. So each orbital of equal energy will have 1 electron before any has 2. And then eventually we fill up the second subshell, and now we have to start a new energy level. So the third energy level gets a little bit confusing in that it has an S subshell, a P subshell, but it also has a D subshell. But what you notice is the D subshell actually starts in the 4th row of the periodic table, or the 4th period. And the reason for that is that it's actually, each of these orbitals, on average, has a greater potential energy. So like the P has more potential energy than the S, and the D has more potential energy than the P. Well, because of that, the third energy level, D subshell, actually overlaps with the 4th energy level's S subshell. So the 4th energy level S fills up before the 3D. And if you can just remember that the D subshell is always 1 energy level lower than it should be, and that the F is offset by 2, you should be good. All right, so then we just keep filling this out. But get the idea that this region over here is known as the P block on the, S block on the periodic table. This right here is the D block. This is the P, and this is the F. And the general electron configuration is you just basically, if you're right here, say we're looking at this element, you would just say, okay, everything up to krypton, we could say it's full. So those rows are complete. So we would just say krypton, and then we would say 5s2, 4d4. There's a couple exceptions you're responsible for, and that includes like copper. These D subshells are much more stable with either 0, 5, or 10 electrons whenever it's possible. So like copper, instead of being 4s2, 3d9, well, the D subshell is very stable with 10, so it'll take one of those electrons from the 4